Hello again. Today's lesson on organic compounds. Yesterday, you should have read through the article, taken the quiz. Even if you weren't getting them right the first time, missing the questions sometimes teaches us something about it. One thing that is commonly misunderstood, and I want to clear up, organic compounds are compounds that contain carbon and are covalent compounds. And all that means for us is, for the most part, they're any organic compound that isn't a carbonate ion. Carbonate, for whatever reason, doesn't count as an organic compound, but it's not actually going to matter to you because the compounds that we're going to work with in this unit are called hydrocarbons. There we go. Okay. And all that means is that they are entirely composed of hydrogen and carbon. Okay. Which means that they're never going to be ionic compounds, and they're never going to have any oxygen atoms or nitrogen atoms, and we're never going to have to care about any of those things, which is great for us because we're going to have to draw Lewis dot structures for these. Now, it has been a long time since we've learned about Lewis dot structures, and before you panic, I want to remind you what they were and then show you why it's going to be super duper easy this time around. So if you don't remember at all, Lewis dot structures are the thing where we said that water was composed of a hydrogen, or that's an oxygen atom bonded to two hydrogen atoms, and there are two unshared pairs of electrons on this oxygen. And the important things to remember was that hydrogen had 2 electrons on it, and oxygen needed to have 8 electrons, and that each of these little dashes, these bonds, represented 2 electrons. So there's 2 electrons here, and there's 2 electrons here, and then there's 2 each of here, gives the oxygenate and the hydrogen 2. So why it's not going to super matter for us is that carbon always wants 4 bonds. There will never ever be any unshared pairs on a carbon atom, and hydrogen will have 1 bond. And so there will never, ever, ever be any unshared pairs. All you have to do is hook the stuff together. So the problem we run into, sort of problem, is that carbon likes to share with anybody and everybody. And it's why there's so many organic compounds out there, is because carbon is the tinker toy of the element world. We can hook anything we want into these 4 bonds. These can bond to hydrogen, they can bond to another carbon, they can double bond, they can triple bond, they can make long chains of carbons, they can make rings of them on chains, and we can have hundreds of carbon atoms, or we could have 2 carbon atoms, and it doesn't matter. They can get really, really complicated, or they can be really, really simple. So this has a whole branch of chemistry dedicated to it because there's so many different things that you can do with just that carbon atom. So I want to show you a couple of ways we can write out these compounds. So we have our good old friend molecular formula, which is the way we have usually written compounds. Molecular formula is what you have done for the last 2 years when you have written out a compound. So we would write something like C3H8. But when it comes to tinker toys, this doesn't really tell us much. Now, this one turns out there's only one option, but if I had handed each of you 20 carbon atoms, you would not all put them together in exactly the same manner. And we need to know which way you put them together because it matters. They're going to behave completely differently. If I handed you 20 Legos, you would not all make exactly the same structure. And that's what carbon is behaving like here, is like that Lego. We can just put these things together all sorts of different ways. So this molecular formula, not super duper useful when we look at how these behave. So what we'll usually use, or the next step, is to go to a structural formula. Which is essentially our Lewis dot structure. We can draw the Lewis dot structure for this thing. So I can write carbon atoms with hydrogen atoms attached to them. Now remember that each carbon needs to have 4 bonds. Each hydrogen needs to have 1 bond. So the carbon is going to be attached to something else. We got to put all the carbons together. Hydrogens will always go on the outside. Simplest thing to do is to put the carbons together and then figure out how many hydrogen atoms need to be out here. Now, the problem with this structure is some of you probably already figured out watching this and you got just eensy bit bored. We're going to get really tired of drawing these hydrogen atoms really, really fast. So the next step, and the one that we're actually going to use the most often, is called a carbon skeleton. Which is exactly like the structural formulas, except we don't bother drawing the hydrogen atoms because they are tedious and annoying. We just assume that they're there. Okay. We simply draw the carbon atoms, bond them together, and just assume that the hydrogen atoms are there. We all know that they're there, and we want to shorten this down. Now, the last type of structure we can draw, we're not going to use very often. We might get to it some towards the end, but this is what you'll use in college classes. Okay, and it's called a bond model or a bond structure. Let's call it that. Okay, and instead of even drawing the carbon atoms, because we're going to get really tired of drawing carbon atoms, and organic chemists get very tired of drawing the carbon atoms, all they draw are the bonds, okay, like that. Now, this is a little bit threatening right now. This is intimidating. To try and picture where these carbon atoms are and where the hydrogen atoms are right now. So we're not going to use this, at least to start off with. Usually you'll see these when they get like a lot bigger. Okay, like here, and we'll have one that branches off here, and this thing might have a big old hexagon attached to it. And every one of these lines represents a bond, and so the ends of these lines represent carbon atoms. But like I said, we're not going there. Okay, we're going to stick with this one right here. But what I want you to do for today, today's assignment, is I'm going to give you a bunch of these carbon skeletons, and you're going to go in and find the molecular formula. The best way to do that is go in and imagine these carbon skeletons being structural formulas. So I'm going to give you a couple of examples right here, so you can see how to do it. Once you get the hang of it, it takes you like 10 seconds each, really, to go through and do these. Okay, so what it'll look like is I will give you something that looks, say, oops, I got crooked. Okay, like this. Okay. And you need to tell me the molecular formula for that. Now, you already know that there are 4 carbon atoms. We just need to know how many hydrogen atoms there are. All of your molecular formulas will be a C, and then a number, and then an H, and then a number, all of them. Okay. So we need to figure out how many hydrogen atoms are on each of them. This one right here, it already has 1 bond. Remember, everything needs 4, so it's going to need 3 more. This one has 1 bond. It's going to need 1, 2, 3 more. This one has 1. It's going to need 1, 2, 3. And this one is going to need 1. So we need 3, 6, 9, 10. So this is C4H10. Okay, pay attention to things, and then some of them will have double and triple bonds. So what if I had a double bond here and a double bond there? Well, this one already has 2 bonds because double bonds are 2 bonds. Okay, so it's going to need 1, 2 more. This one has 2 bonds, so it's going to need 1, 2 more. And this one already has its 4, so it doesn't need any, which means that our molecular formula here is C3H4. And that's all there is to it. Okay,